Now I'm going to demonstrate how to model the second example in ABAQUS. So if we take a look at this geometry, we can notice that this geometry is a cyclic symmetry. So this part is subjected to a rotational body force of 750 units of force per time. And the question asks us to determine the stress values in the part. And the question also asks us to use the cyclic symmetry interaction in ABAQUS to model this problem. So the material used has a Young's modulus of 200,000 megapascal and a Poisson's ratio of 0.3. So the density used for this geometry is line times 10 to the power of lective length unit of density. So since we are going to apply a rotational body force, so we need a mass. That's why we need this density. So if we take a look at the geometry, we can find that we just need to model a sector of this geometry. So this is 30 degrees. So we can notice a sector of this geometry is 60 degrees. So then, 360 divided by 60. So we have it's equal to 6. So the entire geometry is composed of 6 sectors. So we just need to model this sector. Now let's take a look at the dimension of this geometry. So we have 2 circles. So the inner circle has a diameter of 20 and the outer circle has a diameter of 200. And the position of this arc is measured from the horizontal line, which is 30 degrees. And the radius of this arc is 30. Now let's model it in ABAQUS. So I'm going to create a part first. And this time I'm going to use a 3-dimensional model instead of a 2D plane model. So for the modeling space, I'm going to use 3D and deformable. So because we are going to extrude the sketch to obtain this geometry. So here we use solid and extrusion. And here we put 400 because the diameter of the geometry is 200. So now let's use continue. So this time, usually we need to find the coordinate for these feature points. And this time I'm going to model it using another way. So first we need to create a circle. So let's put the center of the circle and hit enter. Now I don't want to input the another point. I just put it randomly. And in order to make sure that the diameter is 200, this time I use this option, add dimension. So I can click add dimension and click this circle. Then we can put it's equal to 100. It's already accurate. But if you want to put it 200, you can use this way. So we put it 100. So the radius is 100. So now let's draw the inner circle. So we put it at a random place. And now I just use add dimension to define the accurate radius, which is equal to 10. And hit enter. So we are going to create a sector of this. So we still need to plot this arc. And the position of this arc is measured from here. So we need 3 lines, this line and this line. so that we can find the position of this arc, and then we need the ending line for this sector. Now let me draw 3 lines from here. So the first line is a horizontal line, then we hit the middle mouse button, and then we draw another line. So we put it randomly on this circle, and then later on we can use add dimension to adjust it. Now we have 3 lines. Now we need to use add dimension to define this angle, which is 30 degree, and hit enter. And the angle between these 2 lines is 60. Now we need to put this arc. So we created a full circle, and then we can add dimension to this circle. So based on the question, the radius is 30, so we put 30 and hit enter. So now we have this geometry. We have some redundant lines. So let's trim it using this option, which is called auto trim. So click this option and select this line, so it's trimmed. And then we also need to trim this line, and this line. So we don't need this part, this line. We don't need this anymore, and we don't need this anymore. Now we have a sector of this structure. So if we take a look at this sector, we notice that this the center of this sector moved. So it doesn't matter. So if you want to move it back to the original place, so you can just use this translate option, and you use select move and select the entire sketch and click down. Now you need to pick a starting position. So this is our starting position, and then for the end point of the translation vector, so you can just put 0, 0 and hit enter. Now this sketch is aligned with the origin of this coordinate system. Now we have done with the sketch, so we just click the middle mouse button and click it down. And this time the software pops up a window asking for the depth, because we created a solid model and we use the extrusion. This is the length of the extrusion. So let's use 20 and click OK. So you can see the depth of this geometry is 20, and this is a sector of this geometry. So next step, we need to define material properties. So we go to the material property and create a material. So first, let's define density. So the density is equal to line times 10 to the power of elective length. So we can put line, and we can define it this way. And next, we need to put the Young's modulus and Poisson's ratio. Young's modulus is 200,000. So we can put 2 and E5. For the Young's modulus, we put it 0.3. So this is equivalent to this. So let's just put it 2 times 2E5, and then click OK. So create a section, solid, homogeneous, click OK, and then we assign this section to this part. Click down, and we only have one section available, so click OK. Next part, we need to mesh the part. So we can use we can put the global seeds. So let's put 5 and apply. So it's good enough. So let's see, use this seeds and click mesh part and click yes. So the part has been meshed successfully. Now we need to select, we need to assign the element type. So select all of them. And this time, you can notice that the software uses the 3D stress. So we can just use the default option and linear, and we use the let's use the full integration. So we can just untick this part. And it's a continuum element, 3D continuum element with 8 nodes. Let's click OK. Now we have the property and mesh. Now let's create an instance. Go to the assembly and create an instance. So we only have one part. Click OK. So next we need to create an analysis step. So we go to create step and step 1, static general. Click continue. So we are going to put the nonlinear geometry on because this geometry is nonlinear. So here we can just use a smaller initial guess, a smaller initial increment size, and click OK. So in order to define the cyclic symmetry, we need to use the interaction option. And we can, if you take a look at this window, create interaction, so you can't find the cyclic symmetry option. That's because we can only define cyclic symmetry in initial step. This is very important. So if you click here and continue, so the software asks you to select a master surface. So let's use this surface as a master surface. So we select this surface. So we click surface and select this surface and click down. Then we need to select the sleeve surface. So we need to select this surface. And we click surface and click here and click down. So now we need to select the first point of axis of symmetry. So before we do that, we need to define the axis first. So we know that the axis of symmetry is the z-axis. So let's just create 2 reference points. The first reference point has a coordinate of 0, 0, 0 and hit enter. And the second reference point has a 0, 0, 1. So hit enter. Now we have 2 reference points. So hit the middlemost button. We are done with this. So let's select the RP1 as the first point of the axis of symmetry, and then RP2 as the second point of the axis of symmetry. And now you can see here we are a window called Edit Cyclic Symmetry pops up. So here we have the master surface and sleeve surface, and we have the point 1 and point 2, which is used to define axis of the symmetry. And here we need to do another thing is that we need to put the total number of sectors. Here we have 6. So we just put 6 here and we click OK. Now the cyclic symmetry interaction has been added successfully. now let's put boundary conditions and loading. So for this geometry, usually we need to fix the inner surface. So let's put encastre for the inner surface. So we are going to apply this boundary condition in the first step. So we select this surface and click down and use encastre, click OK. Next, we are going to apply rotational body force. So in step 1, so we can find the rotational body force is here and click continue. So we need to select the body, so it's the entire body, and click down. So enter the coordinate of the first point on the axis of rotation. So this is because we are going to create a rotational body force. So in order to define this body force, we need to define the axis of rotation. So our force is going to rotate around z-axis. So we can just put 0, 0, 0 here and click and hit the middlemost button. Sorry, hit enter. And then for the second point, so because we are going to use z-axis, so we can put 0, 0, 1 and hit enter. Then edit load window pops up. So the axis of rotation is defined by these 2 points, which is the z-axis. So we are going to use this option. And for here, so the question asks us to put 750 units of force per time. So it's an equivalent rotational force. So let's put 750 and click OK. So once you apply successfully, you can see this error. And the error is increasing. The size of the error is increasing along the radial direction. So now we have boundary conditions and forces and loads. Now let's create a job. So let's go to job and create this job. So this is a cyclic symmetry. So let's click continue and click OK. Then we can submit the job. So click submit. So we can monitor the job. So the analysis input file processor has completed. So it means there is nothing wrong with the boundary conditions and loading. And here we can see our load step has reached 1. So it means the job has completed successfully. So let's check the results. So this is the stress when this part is subjected to rotational body force. So we know that this is a sector, right? So usually we like to show we want to check the stress over the entire structure. So but we only have a part of it. Is there any way to do that? So yes, the answer is yes. So in ABAQUS, we can go to the view because it's a cyclic symmetry. So we can use we can go to the view ODB display option and use the pattern to visualize the rest of 5 sectors. It's just a copy of this sector. So, but for the purpose of for the purpose of viewing the entire geometry, so we can just use this option. So here, because we have 6 sectors, so we just put 6 here, and we use the circular option. So it's around the z-axis, right? Because the entire sector is a cyclic symmetry around the z-axis, and then we click OK. Now you have the entire geometry. Then you can view the stress for the entire geometry. But you should remember that it's just a copy of your sector.